This is a powered milling spindle I built to use in the quick change tool post of my new lathe for drilling and milling operations, and I hoped it would also be capable of milling steel. Oh, I didn't expect that. Definitely one of my biggest projects. I'm glad to have Kiwico on board as a sponsor, but more on that later. You know, normal people start with simple projects on new machines. I guess I'm not normal because I chose something that would kick my machining butt.
Trying to hit tight tolerances and failing multiple times, breaking one or many tools, but also gaining useful side projects along the way. So, how do you come up with such a tool? Well, this lathe tool holder was my main inspiration, because I saw this hole, normally used to hold a tool stationary, and thought,
why not make the tool spin?
That got the gears ticking, and 1 week later I had a 3D model complete.
Besides the holder, the design was mainly driven by available off-the-shelf components like bearings and such. I'll go over that during the build and get started now. This is a lathe project and there will be many turned parts. I'm gonna start with the spindle, the most challenging part of this build, and I chose 4140 steel for that, or this chemical composition. I chose that because it's pretty high strength and gives me the option to harden it later. I've got enough for 4 tries. There's a lot going on, but the first task, and probably most challenging, is I need a hole all the way through. Bought a long drill bit for just that, and coming in from both sides, that should work. Also used for this tool holder, because it also comes with adapter sleeves that turn it into a Mohs taper, which I can then use to mount a chuck, drill with the sled, and make use of power feed.
I try to get the alignment as good as possible, checking with a precision rod in the chuck. As you can see, it could be better. A few bumps against the slightly loosened compound slide, and we are good to go for the length of the drill bit. After that, also indicating the chuck on center. Got it within a few hundredths of a millimeter. So let's begin with the spot drill, followed by a smaller drill. Already here, it's great to use this lead. Super quick retracting to clear the chips. But now, the long drill. Thank God for power feed. Just watching the chips and lubricate every so often. This is everything I have to do, but we need to reach 120mm depth. It still takes a while.
Alright, that's the full 120mm from this side. Went pretty well. I now let the part cool down a bit, flip it around and do the same again. Alright, that went pretty well. There is obviously a through hole now. Let's see if the alignment is perfect by sticking a 10mm rod inside. Oh no, that gets stuck halfway. But that's okay, I didn't expect perfection, and even the tiniest amount of misalignment would cause this to jam. So it's fine to move on, but how did the drill survive? Not too bad, got a little bit hot near the corners, but that's perfectly usable.
Still chucked up like this, I can turn the bore at the end, but of course have to grind down the screw. Target is 12mm, and that's perfectly fine here. Everything else on this part I will turn between centers, so adding a 60° chamfer. And since the threading tool has that angle and is already set up, I gave it a shot. Perfect. Same procedure for the other side, and then I can turn a matching center, which ensures that it runs perfectly true. My part then goes in with a 3D printed drive dog, but not just any 3D print. This is glass fiber reinforced PET, printed basically solid. So stiff, temperature resistant, and a wedge design for good clamping. Thanks Stefan for the print.
I made my drawing such the back edge is my 0, and I can now turn everything up to this shoulder from this reference.
First of all, a bunch of hogging. Checking the diameter front and back told me that the tailstock needed a slight adjustment, about 2/100ths of a millimeter. Next cut. checking, adjusting, next cut, checking, and we're good.
Perfect, within 5 microns.
But before I do the final pass for the bearing seats, I turned on all the other stuff. So the end for the drive pulley, the diameter and relief for the threads, and the relief between the bearing seats. Once the part cooled down again, I retightened the tailstock and did the final pass. 20.02. Perfect, because the last 200ths I can do with sandpaper. Now switching tools for the threads. M20/1 for this nut. So setting up the gearbox for that pitch, painting the surface, engaging the half nut, and go. And a few passes later, the nut fits.
Okay, that's everything of the first setup done, and I can get this out of the centers. Unfortunately though, I screwed it up. I was checking the bearing diameters again, and the back one turned out to be 19.98.
Does that actually make a difference?
Yes, that bearing shouldn't just slide past its seat. I wanted it to be a light interference fit, so light pressure to press it on, and for that it would need to be 19.99 or 20.0. So, I guess I'll have to start over.
I just wanted more lathe practice. Yeah, that's what I'm telling myself. But now with the right dimensions, it's the fit I was looking for.
Next is adding a flange-like part to the front shoulder that will be part of the front labyrinth seal. And I want to make this a shrink fit.
I actually turned the part before the spindle because I couldn't break down the center setup yet. It was a simpler part, but the bore diameter had to be exact to be a shrink fit. 19.98 was my target. Perfect. The rest was just straightforward lathe work and parting it off. Remounted and trued, I cleaned the face and turned a chamfer to the bore.
With the bore being smaller than the diameter it needs to fit, to get them together I need to make this cold and this hot.
I wanted to heat it between 300 to 400 degrees C to expand the bore quite a bit so I can just slide it on without any force. Looking at the color, it seems like I'm in that range.
Perfect. Right now it can still spin, but when it's cooling down it will clamp extremely hard on the shaft. It's getting harder to spin.
But for some reason, it doesn't clamp.
Well, let's say there were problems. Even at room temperature, this ring didn't clamp on the shaft as it should. Because unfortunately, I made this chamfer here too big, as well as the relief cut. So fully seated against the shoulder, the actual diameters that clamp didn't touch each other anymore. And this is the result of getting them apart again. Let's see if I can save that.
The unimportant surfaces I can just clean up with a light cut, but the bearing surface must not get smaller. So I just stoned the tiny scratches and gave it a lick with Scotch-Brite. Still within dimension. Whew.
Yeah, now that's tight. But why do it like this in the first place? Well, otherwise I'd have to start with 40mm stock, which would have been a lot more expensive and wasteful.
Then back in the lathe, I can clean the surface and create a new shoulder for the bearing that's running perfectly true to the rest.
And now all the work between centers is done and I can finish on the other side.
But that requires the forge or chuck. Since every surface is machined, I can clamp between the bearing surfaces where the clamping marks don't matter. Then some quality time with the dial indicator. Pretty happy with a few microns run out. From this side, I turn it to final length and prepared the threads for the collet nut. Then again threading, but with a 1.5mm pitch this time. Eventually, and after some deburring, it's a beautiful fit and we can go to the taper, which starts with a bigger hole. Then I needed to set the compound to 8 degrees, first roughly with the scale, then precisely with an indicator. I'm looking for a 14.05mm displacement when moving the sled 100mm.
I see 14.16. Pretty close.
A bit tedious, but eventually I'm there.
Okay, I moved the sled up to the right dial position and the DRO shows me 100.09. That is close enough. My idea with the taper is to now cut it roughly, since the spindle isn't running perfectly true in the chuck, and later, when it's mounted on its own bearings, grind it to final size and shape. So then it's running perfectly true to the bearings, and that's what matters.
In theory, I now just cut the taper, but reality doesn't like the stick out and the surface finish looks like shit. Maybe a sharper insert. Better, but not great. At least the angle is correct. Eventually I found feeds and speeds that were okay-ish.
Now size-wise, I'm basically copying this spindle by using a collet, sticking it in and measuring the stick out. And then I turned on my taper until the stick out is the same. There's quite a bit left. Yeah, that's enough. Rest then is for grinding, which is also good because the surface finish isn't that nice. But chucking up a bit is already possible. But I hope the runout will improve when I grind it in.
Maybe I should grind the chamfer too, cause that doesn't sound good. But that's all round work complete.
So far so good. There are two more features missing, the keyway in the end and the wrench flood in the front.
For the keyway, I lightly clamped the shaft in a suited tool holder and set it on center with calipers. End mill in the chuck and go. I didn't have the right size end mill, so I had to do 2 more passes with the part off center. A bit more work, but eventually the key fits.
You know, that would have been a perfect job for a dual post milling spindle. The wrench flood I'm gonna file by hand with a simple jig.
It's 2 3D printed squares that fit tightly on the bearing surfaces and 2 blocks of wood that limit the cutting depth. It's slow, but simple and accurate. And it also scratches up the table real good. Doesn't matter, cause it's a workbench. Once the file is at depth, I can flip the part for the second side. To sneak up on the size, I put shims under the prints and continued filing until...
And that's the spindle complete. Next part is a lot simpler, the spacer bushing between the bearings made from some tube material.
It needs a little bit of machining, but way less. Basically boring the ID until it just slips past the bearing seats. You can't see it, but most of the inner diameter got relieved and only the ends are precise. Then again a 60-degree chamfer on the ends to put the part between centers and turn the OD true to the bore. I edited it out, but this was the incredible soothing cutting noise. At least the surface finish is great.
And now with the main shaft and bearing spacer done, let's talk bearings for a second. As a milling spindle, these bearings need to handle different kinds of forces. Milling sideways, we obviously have radial loads, but we can also plunge mill and have axial loads. But not only that, due to a spiral on end mills, it can also pull. So we have axial loads in both directions. We of course also want super low runout, no axial play, and I intend to also use this as a grinding spindle, so high RPM. Up to 30,000 is my goal. And with these requirements, there's only one suitable bearing type left. Unfortunately, it's very expensive because we are talking angular contact spindle bearings. Actually, 2 of them mounted as a pair in an O configuration. What that means and what they are is easier to see in a cross section. These bearings are made such the bearing balls contact the inner and outer race at an angle. In my case, 15 degrees, hence the name angular contact bearings. That's great for taking axial loads because they travel along the contact line into the housing. With a regular bearing, axial forces would travel much shallower up into the housing and they couldn't take that high of a load. They're pretty much always used as a pair to take loads in both directions, either in the O configuration or the X configuration. The O configuration has the advantage that it shifts the point of support outwards as if the bearings would be mounted apart from each other, making the whole construction stiffer. What these bearings also have is ground-in preload when mounted as a pair, which means when they are mounted and pressed together, there's a certain amount of preload suitable for my application. And that means I don't have to mess with any other preloads. Pretty cool. On a surface plate, you can actually see the ground-in preload. Like this, spinning on the outer race, the inner one spins as well and rubs. But flipped around, it stays still and the bearing bolts work. Compared to a regular bearing, it behaves the same both ways. And that's because here, this surface of the outer race is just a few microns higher than the one of the inner race. And that's what creates the preload when they are pressed together. The front bearing's taken care of, the back one can be much simpler and cheaper because it doesn't see any of the cutting loads, only the radial load from the belt tension, and it needs to handle the high RPM. So the next part to make now is obviously the housing, but there's one tooling side project that needs to happen first. It's basically this router that I want to mount in a tool holder as well. So I'm gonna make one from this round and precision bar stock.
Facing and cleaning the OD is straightforward, and a beefy chamfer. Then boring the hole slightly undersized. Since I set my compound to 45 degrees, I can cut the chamfer on the other side while parting off and saving time. And that's me underestimating the weight of this part. Now cutting a length of the precision bar stock and preparing for welding. I can center the parts to each other with a couple drill bits in one direction and with bearings that had the right diameter in the other. A quick tack on each side and I'm ready to weld solid. This is 10mm and this 20mm thick material. The max my welder can do is 170 amps, so that's what we're using.
You know, I'm pretty happy with that. The idea now is to mount this to the faceplate, machine it to final diameter, and then add bolt holes and a slit for clamping. However, due to the high heat input from the welding, there's probably now a lot of stress in the part, and when I cut the slit, it could distort and then no longer fit. So before machining, I'm gonna stress relief anneal it in an oven I could lend from Stefan at 560 degrees for about 3 hours. And while that's baking, I can pretty and true up that faceplate.
This cut makes very good use of the constant cutting speed feature, which means the lathe speeds up towards the center.
Much better.
I still had time and cleaned up the bore as well.
Well, I didn't know what to expect, but that's the part now, and I could go on machining, but there's yet another problem. I assumed this precision bar stock I bought would be square, but it's not. And I have a possibly dumb idea to correct this. This cutter is for woodworking, so the cutting angles are all wrong for metal, but it's still carbide and harder than steel, so...
With the part clamped in the tool holder, I took a light pass along the edge that will be clamped to the faceplate. This won't necessarily make it square, but a line to the faceplate, and that's what counts here.
Well, I would say that worked pretty good.
I did the other side as well, cause I might also use this tool and this orientation. And here you can clearly see the out of squareness.
Now I can get this out of here and mount it to the faceplate. Except this needs a couple more mounting options. I hope a bunch of M12 threaded holes are enough.
I then set up a dial indicator to get the hole aligned within a couple hundredths of a millimeter and gronked down the bolts. So let's get this board to size. This better not move out of position. Since I can't run the lathe at the proper speed, the surface finish isn't great, so I tried switching to a sharper insert and that helped a lot. And that's the fit I got. Pretty happy with that. So I cleaned the face as well and chamfered the inner edge.
Whew, quite a bit nerve-wracking, but I'm very happy with the fit, so can break this down again.
I also couldn't resist facing the other side as well. I now just needed to add the holes for the clamping bolts, which I could all do with the part in the tool holder and the tooling in the chuck. So basically, a sideways mill. I don't have an elegant way for the slit, but the saw will do. If the stress relief worked, I should now still be able to install the router.
Pretty tight already, and less than a quarter turn to tighten it. Cool. What a side project, and I'll need it in a minute for the spindle housing, so let's get started with that. Material-wise, I went with C45, nothing special, but cheaper and easier to machine, and I bought 2 attempts.
Oh, what a wise decision. At first, I have to turn the OD down to 40mm, which means some heavy hogging. Let's see what the machine is capable of. 1mm depth of cut, no problem. 1.5mm, easy. 2mm, come on. 2.5, not breaking a sweat. But the floor, of course, gets covered, as well as myself. Looking familiar to somebody? I left 1mm for the finishing cuts and took care of roughing the bore before that with a U-drill. I know it has been around for a long time, but it's still hard to believe that it's capable of plunging a 25mm hole just like that. The chips it produces speak for themselves. I needed to plunge in all the way, and once done, I could use it like a regular boring bar for further roughing.
What an amazing tool. Unfortunately, I don't have coolant set up, so everything is quite hot now, and I let it cool down before I go on.
I then finished the bore with a normal boring bar and went back to finish the OD. Not the best method stiffness-wise, but I didn't want to wait for cool down twice.
Checking dimensions, I get 40.01 here, 40.01 here, and 40.03 here. So not even, probably because of deflection from the tool pressure.
But with the lathe bed covered, I can sand the fit to perfection.
Okay, now I'm reading between 39.99 and 39.98 everywhere. Exactly what I wanted. Perfect. Let's go on.
Next, I faced the end and then the shoulder to dimension. Neither you nor me can see it, but I then prepared the ends for the threads. So turning this diameter, the thread relief behind, and then the bearing seat. I want it ever so slightly bigger than the bearing OD. Just like that.
And that's the finished bearing seat. So last missing are the threads at the end. But the clearance is small, so risk of crashing is high. And that's where this comes into play.
I'm gonna use it with a thread mill. This allows me to just set up the right thread pitch, engage the half nut, and let the lathe spin as slow as possible, giving me plenty of time to react. Having scratched the surface, it's go! It's not full depth at once, and I only had one cutter, so it's still multiple passes.
And there are the finished threads, totally risk-free. Actually, with this method, I could go with a lot less thread clearance.
That was all of the first setup.
How's the fit with the holder? Nice, and tightened with just a quarter turn. Oh, perfect.
Before the second setup, the excess material can go. I have my part safe in the chuck and the offcut will fall off. Okay, now switching to the forger chuck to remount the part for the second side.
To protect my nice surface now from the chuck jaws, I put some softer aluminum pieces in between.
There's a small turned section from the first setup that I can now use for indicating. I got it close, then switched to a test indicator and got it to almost 0. First facing to length and using the shoulder as reference. Then there's a bunch of internal hogging, perfect job for my new favorite tool, the U-drill. The features are again internal threads and a long bearing seat. So after roughing, I again switch to the boring bar to prepare the threads and then sneak up on the precise ID. Let's see what we got. Bearing is this, and my seat is, oh no, overshot. Why? I was so careful the entire time and screw up the most important dimension. Well, maybe it will still work, because it's still an interference fit. So I moved on with the threads, just like before. Cleaning up the OD, and then finished the through bore. So letting the U-drill punch through, and then turning to size. A last-minute decision was to add 2 decorative grooves to the OD before calling it finished.
Sanity check. The spindle fits through. Good. So this part is finished. Everything looks nice and well, but this slap from reality tells me I need to start over. These bearings must not just slip in like this. Well, that's what I bought the second attempt for. Now I have 2 identical twins, except this one has a 2/100th smaller hole and is usable. What a weird thing to say. The next parts are the housing caps and the spacer, and they all have one lathe operation in common I haven't done before: trepanning.
Trepanning is an axial grooving operation that I need on my parts to create a labyrinth seals. But before we can get to that, the rest of the part needs to be turned. This will be the front cap, so I started with preparing the outer threads with the major diameter and clearance, followed by the hole where the spindle fits through. It's amazing every time how this U-drill can just plow through the material. I then open it up until the spindle threads just slip through. Next adding chamfers, and then the threads with the tool feeding away. A couple passes and the housing fits nicely. Now removing a bit more material and we can move to the trepanning tool. It's actually pretty tiny and looks even smaller in the tool holder. Here we go. Working pretty well. I just hope it doesn't break, because I only have one of... No. Oh crap. Why? Why?
This sucks. Let's switch to plan B. Plan B is tiny end mill in the router.
Being even smaller, I didn't know what to expect, but I just touched the wall and face to find my position again and went for it. A 0.1mm deep cut, no problem, but eventually it'll be the full width where the other tool broke. Right about here. Seems to work. Amazing. Then another finishing pass and moving to the inner diameter. Well, other than 1,000 needles sticking in my fingertips, this worked great.
I don't have a good way of measuring the inner diameter now, but I have the failed flange from the shaft before, and it just has to fit all the way in with a little bit of play. Like so. Nice. Whew. What a fantastic side project.
But the part is not done. And spoiler, it gets hot during cutoff. Don't let it touch your skin or you might panic and launch it on the floor.
It was hot.
Told you so. But the parts fit together, forming the seal.
Screwed on, I put it back in the chuck with aluminium as protection and can now finish the face and chamfer.
Both straightforward, as you can see, but your experienced machinists may see what's about to happen with the chamfer.
Shit. Right, it will unscrew. Well, now it's stuck. I don't know if it's damaged and I can't get a good grip on it. The last missing feature are the holes for the pin spanner, so I just have to do them now and try to get it off again.
So into the holder it goes and then spotted and drilled.
Let's see if it comes off. It's not moving a bit. Moves. I guess there's a chip in the threads. Hopefully that won't damage them too much. All right. Yeah. Chip in the threads. This project is quite nerve-wracking. The threads are damaged and I cannot make another housing. They need to be repaired.
I aligned it back in the forger chuck, did my best to find the thread again and made a couple passes. It chipped an insert, but the threads are saved. My efforts for the cap were unsuccessful, so here I made a new one.
I'm back at the state of a few hours ago. This time I'll do it right.
So facing from this side and chamfer from this side too. Good. The holes are the same as before, and this was how I wanted to show the finished cap in the first place.
Oh dear, I hope these will have less hiccups.
Let's see. The back cap is pretty similar. Turning stock down, making the bore, then the threads along the entire OD. And then the trepanning, or whatever you want to call that. Yep, that bit broke. At least here I had a couple more. And look, I also learned to use the tailstock for catching the hot part. Screwed in, I could also face it to find length and drill the pinholes like before.
Too easy.
The last part is more of a bushing with the trepanning on the outside so we can better see it. Sped up, you can see how much the tool deflects. Amazing that it can do that. Looks good.
Man, these parts taught me a good number of lessons I'll definitely never forget. Especially since I had to make almost every part twice. But you know, failure is a good teacher. I'd also categorize this project as quite advanced, and the skill for designing and fabricating these parts of course came from my engineering degree and a furious experience. But the foundation and general interest in mechanical designing came much earlier during my childhood. And I would encourage everyone to tinker around with mechanics at a young age. A great helper there is this video's sponsor, Kiwico. Every month they deliver a crate with exciting STEM projects that inspire your kids or yourself to explore, build and create. All hands-on projects, and next to failure, one of the best ways to learn. Kiwico offers 8 subscription lines for all ages and interests, so there are other options if mechanical design isn't your thing. I really enjoyed building a crate with each of my two nieces and seeing the joy in their eyes while building and learning.
I also had some fun myself building this table tennis robot. And the safe with a working lock.
Every box not only contains the parts and manual, but also a magazine to dive deeper into the topic and really understand the presented concept. And really understanding a concept sets the foundation for applying it elsewhere and practicing problem-solving skills. So if you want to give your kids or yourself the same kind of experience and the chance of building skills and a passion for creating, check out the Kiwico subscriptions at kiwico.com/Marius in the description. And you will save 50% by using my coupon code Marius at checkout. And now back from their assembly kits to my own one.
As a last-minute decision, I threaded the spindle end with M12 and cut 2 slots along the end. Could be useful.
Now the first parts to install are the front bearings, and they need to slip past the back bearing seat, which is also a light interference fit. So that would be easier if the bearings would be slightly bigger. Let's try that with heat.
95 degrees C is within the bearing specs, and a touch of oil also can't hurt.
All right, here goes nothing. Perfect. Okay, here it's tight. But now I can use a bearing dummy and the nut.
Well, a wooden hammer and a sleeve were quicker.
All right, that's fully seated. And the second one. Good. Ah, perfect. That's what I wanted. Just slips on. No hammering needed. And now I can already put pressure on it with the nut. Both bearings fully seated and alight and spinning super freely. Next, this goes into the housing, and it would also be easier if the housing was bigger.
So that went into the oven at 200 degrees C. How much of a difference does that actually make? This is the bore at room temperature, and this at 200 degrees. So the spindle should just drop in.
Hot and tasty. Let's see. Perfect. Just drops in. And I can close the lid. And that will press them down for good. But I can't really grab. It's hot. And this spins super freely, so the labyrinth seal touches nowhere. And the gap between the spindle and lid is as small as designed. Now I quickly put it in the tool holder to get rid of the heat more quickly. This is now also a tighter fit, of course, because of the heat. And also pretty cool to see already, with just the front bearings installed, no back bearing, and indicating in the back, I can see about 1/100th of a millimeter runout. That is really good. And also relatively stiff when I'm pushing here, with the bearings being here. But I hope the heat from the housing didn't damage the bearings. Well, there's no non-destructive way to check, so I just hope. To also apply a little bit of preload to the back bearing and remove the play, I have this wavy spring washer that will apply a little bit of pressure to the outer bearing race.
It just drops in together with the bearing spacer. I again preheated the bearing and the back part of the housing.
Let's go. No, this doesn't want to go. But that's what I got the nut for. The actual spacer. Now until it's tight. All right, still spinning freely, and we're bottomed out. Beautiful.
Cooled down, I opened the back again to lubricate the bearing.
For lubrication, I'm using this bearing grease, suitable for high RPM. And now for the speeds I want to reach, it's recommended to fill the gaps in the bearing to about 30 to 40%. And I can just do that visually, kinda. Let me know if I'm doing it wrong. But that would be it. So now the spacer and labyrinth seal part 1 can go back on. Then the housing lid, which is also labyrinth seal part 2. It just screws against the housing, not the bearing. The bearing is this nut again, with my improvised 3D printed wrench. And that's the spindle done. Would you believe that this is half the project? This needs to be powered, so let's get to that. I found this nice little 750 watt servo motor that comes with a speed controller and can range from 200 RPM up to 7,000, and also a direction switch. Perfect for my application. It's actually sold as an industrial sewing machine motor, but it can be used for anything. Linked in the description. It'll get mounted on top like so, with some kind of plate that clamps on the back part of the housing here, and then connected with a belt. But of course, it's never that simple. If I want 30,000 RPM here, even with this spinning at full speed, I'd need a pulley ratio that looks like this. And that's not gonna happen. I of course also want a setting for lower RPM but high torque, and then a in-between kind of setting. So to get all of that under one roof, I opted for a 2-stage pulley design.
I spare you the details on what went into that, but to summarize, designing useful 2-stage pulleys like on a drill press isn't easy. I made a table to play with the pulley ratios and a model to visualize all belt combinations.
Maybe I go into detail about that in a second channel video, but for now I'll get these different spindle speeds and need to make these 3 pulleys, for which I have to grind a special tool from a high-speed steel blank.
Actually, not too difficult. It's a 40-degree tip, so I removed the bulk with a small grinder while keeping the steel cool with water and got the general shape ready. The rest I then did on the whetstone sharpener, with a few 3D printed jigs for setting the angles. I just winged most of the geometry as well as the tip radius, but looking at it under a microscope, I'm happy with what I'm seeing.
Not too bad. Let's see how it cuts. I mean, it's a bit noisy, but it cut the profile.
Now, starting with the spindle pulley, turning it from a big bar of aluminium. First removing my test cuts, and then start with the most critical feature, the bore. I don't have aluminium inserts for the U-drill, but it doesn't seem to care. Then I turned it to a perfect fit with the spindle.
Ah, nice.
Next, hogging away the material for the pulley steps. That's just fun with aluminium. Then switching to a pointier inserts for the finishing cuts and get sharper corners. Now my V-groove tool. There wasn't a good way of aligning it, so I just eyeballed it. The rest is simple. Cut, move, cut, move, cut, move. Cut, move, cut, move, cut, move. Cut, move, cut, move, cut. Just following the drawing dimensions. I then filed away the sharp edges, added chamfers, and cut it off. For the bore on the other side, I could only use light pressure from the chuck and light cuts to not damage the grooves. But I seem to got the balance wrong.
Shit. No actual damage.
Fortunately, it didn't matter and the part is complete. The motor pulley is much the same, except the bore has an undercut that nobody can see, but this is what happened.
Essentially what I did was move the tool in position, then plunge in, or rather out, and then move it back to remove this material here. There you can see it.
Then just more hogging, finishing, and grooving. There's a bit more meat left at the end before cutting it off, but that's the motor pulley done. And it gets mounted with a custom nut that I, surprise surprise, turned, but also milled. Last one is the idler. That's slightly different because it'll have bearings installed, so I turned a proper fit. And since it's reversed compared to the other ones, I hogged away the material with the cutoff tool in this setup.
To now cut the belt grooves on this one, I turned a mandrel where this perfectly fits, and I can mount it the other way. To reach the smaller diameters here, I need quite a bit of stick out of the tool, so I put a second blank underneath for more support.
But then it's the same as before.
Now what the spindle and motor pulley are still missing is the keyway to transmit the power. And for that, I need another special tool.
And what I'm doing is follow a Blondie Hacks video about broaching keyways with the lathe. It's a relatively simple cutter shape that I again roughed with the grinder and finished with the whetstone. To make it a bit smaller, I removed the edges a bit and then cut it off short, cause that's all I need. The cutter goes into a holder that's basically a rod with a cross hole and a threaded end for a clamping set screw. That's how it should work. So I set it up in a tool holder, pulley back in the chuck, and here goes nothing.
Ah, first chip.
I went with about 0.05mm depth per pass, and seeing the chips curl up like this is a good sign that my tool geometry works well. Also, the cutting noise sounds, I don't know, it sounds right. So mesmerizing.
Now I'm at depth, but unfortunately the key doesn't fit, because unfortunately my tool turned out 4/100ths too small.
But that doesn't matter, I just raise the tool by that amount and do more cuts. Now I get tiny shavings.
And now the key fits perfectly. Let's also check with the key in the spindle. That works. Oh yeah. Now I can cut keyways. Let's get the other one done and move on. Perfect. Now you can also see the purpose of this undercut. It was room for where the tool exits the keyway. The idler pulley doesn't need a keyway, but still needs a shaft to spin on, and it's also the one that will tension the belts. And for that all to work, I need a few more turn parts.
By now we have seen so much turning, so I go over these parts quickly. This is the idler shaft for the bearings, which also gets a reamed through hole. Always nice to play with. And a precise diameter on the other side. The second shaft is for tensioning, and at first it gets turned down to a sliding fit with the previous shaft. The end gets some threads, which I could once again do with my side project. Oh yeah, I also turned this knob before that I need. Then, with still a lot of meat attached, I clamped the part in a tool holder to drill the M6 cross hole that will be used for belt tensioning. And then the other side gets turned down to a precise diameter as well, and some more threads. There's actually a few more parts, but I'm sure you can guess how they were made.
And now assembly, starting with the bearings.
They are again a shrink fit to never come loose, so baking the pulley at 200 degrees C.
While that's heating, I can prepare the bearings for assembly, because there's an inner and outer spacer. Second bearing on top. This now goes into a shoulder bolt with this part before that I turned to only press on the outer bearing race. Stacked like this, it will be easier to install all at once, and with the threads I have the option to clamp if necessary. That is not going in. That is pretty bad. Second try. Okay, so much for that. Second try 2.1. Can also hammer it in. Yeah, not the most elegant way. But now I can use the screw. Oh, that's actually really tight. Okay, bottomed out. Bearings are in. And that hammering was all fine because I only hit the outer two races thanks to this piece and the bearing spacer. Well, bad news. It's cooled down again and the bearings are not smooth anymore. They're quite stiff. So either the hammering did damage them or the shrinking now clamps so hard on the bearings like pressing them together. Either way, this won't work.
Nothing to lose, so let's press them out again.
Well, bearings removed. They're still fine. So this was too tight of a fit.
I could remount and open the hole by 200ths, and thankfully, past me also ordered more bearings, so next attempt.
Ah, that's how it needs to be. No further clamping, just let it cool down. Another block of aluminium should make that quicker. Now it runs smooth, the part is saved.
There are two more shrink fits. One is a flange-like disc for the bearing shaft.
Let's use the screw.
The other one is a flange-like disc for the tensioning shaft. Although this one also gets secured with a lock nut.
I like shrink fits. Not the best execution here, but an elegant way to attach big flanges to small diameters. Next, I press the pulley on and I put a small layer of Sharpie where the bearings are, because the fit before wasn't as tight as I wanted, and the Sharpie adds just a little bit of thickness. Now tightened, it still spins freely, and in use will get clamped by this knob. Nice.
So now I have the main spindle with pulley, secured with the set screw that I added last minute, the motor with pulley and clamping nut, and the idler pulley assembly, which probably doesn't make too much sense at the moment.
But next I'll bring everything together with the motor mounting plate, and then it'll make sense.
There's a lot going on, so I 3D printed at first to verify that everything fits.
It clamps around the back of the spindle housing, motor screws to the top. The belt tensioning bolt goes through a slot here where it meets with the belt tensioning shaft. And the idler goes on top where it's then free to move in this range. So let's get some belts attached. Now tightening with this screw. I will later replace this with a knob as well. And once tensioned, tighten this knob and go.
Finally, seeing it moving.
Okay, that was the slowest setting. Let's try a higher one. It is a bit scary standing next to it, but it runs super smooth. Of course, it's still wobbly with the 3D print. But what I'm seeing so far is great. There still are a few things to iron out. For example, I cannot tension every belt setting at the moment because the idler is bottoming out. And I need to add a lid and whatnot. That's why I opted for 3D printing. That's quick to iterate. And we are at version 3. Okay, now I can tension all the belt combinations. There's still a few things here and there to tweak, but once that's sorted out, I can machine the plate from aluminium.
So on to the CNC router for machining. At first I clamped it with hold downs and let the machine punch some holes for some direct down bolting. The problem now is that CNC is boring to watch, cause the machine just goes well, except for the roughing. There the chips are flying. Then of course a tool change. And the chamfer bit.
Still clamped secure. I'll check the hole dimensions to make sure it fits the spindle and motor. Motor side looks, well, spot on, but that will be too tight. And spindle side, looking for just over 40, and I'm getting, oh, quite a bit less. Yeah, that I need to open up by a bit more than a 10. My failed housing has a use. That's the fit I'm looking for.
And that's all the CNC machining done on this part, but there's some more manual machining necessary, like freeing the part and chamfering the bottom edge, which works well on the woodworking router table, then some threaded holes and the one for the clamping bolt, and then the difficult part, this slot in the edge for the tightening bolt. I didn't have a good plan, but started with a series of intersecting holes.
So far so good, the rest is hand files and patience. After a while of filing, I thought, could the Panther router also cut this slot? And
the answer is absolutely yes.
Well, it's not the nicest result possible, but the slot is totally there, and that's what matters. I didn't have to file.
So now it can all come back together.
It's so nice now with everything being solid and nice and smooth. There's of course one more part missing, a belt cover. I don't want to get my fingers in there. And that is the last part missing before we can test it out and do the first cuts.
The cover will not only cover the belts, but also hold the speed controller, since dangling like this is no long-term solution. It's a complex part, but straightforward for a 3D printer.
There's a little bit of support structure I need to remove. It turned out quite nice, and I had to print it like this with the support structure to get a nice and smooth outer shell. It goes on like this, can hinge open for belt change, and I'm pretty proud on my hinge design.
It's two small prints made from high-strength material, which get two melt and threaded inserts installed and the pinhole reamed. There the hinge pin fits, and together it goes straight into the cutout in the aluminium and is secured with two screws. The cover has matching cavities and 4 screws secure it.
Oops. And fixed.
On the inside goes a bigger pin, which together with this clip snaps the lid shut. The motor controller goes on the outside, where all buttons are easy to reach and the cables are out of the way.
It is complete. Let's try it.
Chucked up an 8mm end mill and some steel. Let's go.
My lathe can now mill. And for the first cut with the random feeds and speeds, I'm happy with what I'm seeing here.
Another cut sounds much better.
Much happier sound this time. Lower spindle speed.
Oh yeah. This is awesome.
Let's push it some more and go deeper. Looks and sounds like it also handles that pretty well.
Oh, I didn't expect that. That just was an 8mm deep cut. And it did it just fine. It was supposed to only be 4mm, but I didn't tighten the collet enough, so the bit pulled itself out and cut deeper and deeper. But the spindle didn't care. That's pretty amazing. Now to round this project off, I'm gonna make a little hand crank for the belt tensioning bolt using the spindle.
It's 3 relatively simple parts, but all of them make use of the milling spindle. At first, just some turning and a reamed hole. And then cutting across. Also, this material was a 10.9 grade bolt, so pretty tough. Then flip the chuck 180 degrees with the help of a digital angle gauge and cut again. Next, changing the cutting height and do 2 more cuts.
A nice little custom washer that won't spin in the slot.
Second part is the hand wheel from aluminium, so first again a bunch of turning. Then I need a threaded hole 13mm off center. So I touched the part's edge to find the center, moved into position, and then basically drilling as usual.
Okay, now I want to press this hex head bolt into the center, and to be able to do that, I'm gonna mill a hex pattern with a tiny end mill.
Making use of a higher RPM and plunging straight in. The digital angle gauge is again perfect for the hex pattern.
A bit more. I guess a hammer will do the rest.
I then also milled the edge and cut it off. Nice result.
So let's try to fit the bolt. Pretty sure that'll stay in there.
The last part is the spinning knob from some brass, which also gets a reamed through hole. Then I needed to open up the top part of the hole for the bolt head. Next use case for the spindle. And with a bigger bit, I milled some decorative scallops in another hex pattern. Finishing the knob shape, and we can go to assembly.
Well, there is a fourth part, but that's just a bushing without any mill features, and the assembly is a single screw. Nice spinning knob. Much better. And that makes belt changing tool-free. So far all my use cases were with the spindle oriented like this, but I can also orient it like this and drill cross holes or mill keyway slots.
By the way, this material is stainless, which the spindle handles just well.
What a versatile tool. It's gonna be incredibly useful. Now, early on I mentioned I wanted to grind out the spindle taper once mounted in the bearings. I'm gonna save it for another video because I'm not done with this project. There's the spindle through bore that obviously is for a drawbar to attach accessories like a grinding arbor, a drill chuck or other accessories. Any ideas? So this project will continue, and the last thing I want to try now is crank it up to 30,000. And whatever happens, happens.